Okay, so let's jump into this deep dive. We're looking at the rules for FuzzNet Labs. It's this competitive game where players are basically data scientists building a service to identify cute animals.
Right. And it looks fun, but what we really want to do here is break down the rules, the setup, how you play, scoring, and connect every single piece directly to how real neural networks and, deep learning actually work.
Yeah, the goal is you'll understand the game and get a feel for building an ML model. Because
Mhm.
the game really simulates building a deep learning model, which is a type of machine learning, or ML itself, a part of AI.
Exactly. It's a clever abstraction.
So setting up,
Let's start with the shared stuff. The components everyone uses laid out in the middle. We've got data tokens, node tokens, and these things called overfitting tokens.
and placing the scoreboard is interesting too. You flip it based on the number of players, 2, 3, or 4.
We've got the shared resources sorted. Now, what about our own setup? The individual player stuff.
Right, this is where you initialize your specific model. Each player gets a player board and these little animal tokens in their color.
The animal tokens, those are the cute animals we're trying to classify, like cats, dogs, bunnies, whatever.
Exactly. They represent your specific classification targets. Now, first, you figure out who goes first however you like, dice roll, cutest pet picture, whatever. They get the first player marker.
Standard stuff. But then the setup gets specific.
Very specific. The first player takes all 5 of their animal tokens and places them on the rightmost column of their player board. Any order they want down that column.
Okay, they choose their initial lineup.
But here's the kicker. Every other player then has to arrange their animal tokens in the exact same order on their boards.
Wait, really? Everyone starts with the identical animal order. That seems counterintuitive for a race. Why force everyone to be the same at the start?
It simulates a really common real-world scenario. Think about it. Lots of AI startups might begin by using the same foundational model, maybe a big open-source language model or a standard image recognition framework like VGG.
Ah, okay. So you're not competing on the absolute basic blueprint initially.
Right. The game forces you to differentiate later through how you train the model, how you add complexity, not by having some secret initial structure. It's about execution.
Gotcha. And part of that initial setup is also this data clean token, right?
Mhm.
Everyone puts it at the top of a track on their board.
Yep. That token represents your, let's call it your intervention capacity, your ability to maybe fudge the results a bit later, re-roll a die, flip a result. Think of it like manual data cleaning or emergency fine-tuning. But the interesting bit, turn structure.
Oh, yeah, it's key.
Your very first turn, you get 3 actions. Kind of lets you lay a foundation, but
Yeah.
then every turn after that is just one single action, clockwise.
And that really forces you to think ahead, doesn't it? You can't just build everything at once. Your first action choice is usually design model.
Explain that. You add a node token to an empty spot on your board.
That's basically you deciding on the architecture of your neural network. Specifically, you're setting up the hidden layers, each one of those node tokens. It's like a neuron.
So more nodes, more neurons.
Pretty much. A bigger network, more nodes, well, that can lead to higher accuracy. But, and this is a big pay in it, but it also ramps up the cost and time needed for training. It gets complex fast.
Okay, so nodes are neurons. How do you, feed the network? How does it learn? That must be the next action. Train model.
You got it. Train model lets you add 2 data tokens onto your placed node tokens. And crucially, these data tokens, once placed, they can't be removed. Each one adds a +1 bonus later.
So you're feeding it information.
Precisely. This mimics supervised learning. Imagine showing a model a picture of a cat and telling it this is a cat. The game represents that labeled data with these tokens. They directly influence the probability of success when you test it.
But there's a catch with training, right? The game calls it overfitting.
A huge catch. A single node can only hold a maximum of 3 data tokens if you max out a node like that.
You get an overfitting token, and you have to place it on a path leading away from that maxed out node, blocking that path permanently.
And that's overfitting in a nutshell. In the real world, it means your model got too good at recognizing the specific training data it saw. It memorized instead of learned.
So it can't generalize to new, unseen data.
Exactly. It loses flexibility. The game gives you a tiny +1 point bonus for a max node, maybe representing hyperspecialization, but that blocked path, that's the real cost. It physically shows how bias can just shut down parts of your network's potential.
Okay, so you've designed it, you've trained it, maybe risked some overfitting. Now, test model.
Time to see if it works.
You need to find a path 3 nodes with node tokens on them, connecting an animal picture on the left side of your board to its matching animal token on the right. Then you roll 3 dice.
And here's the core mechanic for testing success. The total of your dice roll plus the number of data tokens along that specific path needs to hit 18 or more.
Not just roll high, but hit that threshold with your training data helping.
Right. And that target number, 18, not being, say, a perfect score, is important. It simulates giving the model a new photo it hasn't seen. Real ML systems aren't about 100% certainty. They are, by design, probability machines. They give you the most likely answer based on the data.
Makes sense. Now, there's this optional rule, which honestly feels like it should just be part of the main game if a test fails.
Ah, yes. The rule where you have to move one data token somewhere else on your board.
Why is that so significant, moving data after a failure?
Because that, right there, is the game's simplest, clearest representation of backpropagation. The network made a mistake, the test failed. So the system adjusts.
Learn from the error.
Exactly. You're tweaking the internal weights, how the training data is distributed to try and do better next time. It's the core feedback loop of learning in neural networks, built right in.
Clever. Okay, but what if your dice rolls are just awful or your data isn't quite enough yet? There's the clean data action.
Right, your lifeline. Before you figure out if a test passed or failed, you can use clean data. Lets you either re-roll any number of your dice or flip one die to its opposite side. A 1 becomes a 6, 2 becomes a 5, etc.
Sounds powerful. Too powerful.
Well, it simulates having to manually clean up messy input data or, directly intervene in the process, which is costly and time-consuming in reality. And the game reflects that cost.
How so?
Every time you use the clean data action, and you can only use it 4 times total, you slide this token down a track. And that track means negative points at the end of the game. First time is -1, then -2, then -4, then a whopping -6.
Ouch. So you pay a steep escalating price for manually fixing results instead of building a better model through design and training.
Precisely. It discourages shortcuts.
So scoring it all up, you get points for each test you pass. You take the highest available point value for that animal from a central board. You get +1 point for any nodes you maxed out, the overfitting ones, and a bonus point if you manage to test all 5 animals. Then you subtract whatever penalty you racked up from using clean data.
And the game ends either when someone successfully tests all 5 animals, or if players get so locked up with overfitting so many blocked paths that testing just becomes impossible for anyone.
It all seems to circle back to that idea you mentioned earlier.
Yeah, that core concept. Data is destiny. The whole game reinforces it. Your network, your model, it's only as good as the data you feed it, both the quantity and the quality. Shortcuts like clean data are punished. Overfitting cripples you.
It really drives home how fundamental good data is for any kind of AI or ML system.
Absolutely.